Right, well, welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. And a very sunny evening it is here too. I hope it's nice where you are. Tonight, let me leave the slides on. We have, I'll just do one or two welcoming notes, and I'll talk about what's coming up in the future. Then we have Petri who's going to talk about the South African Large Telescope and the South African Astronomical Observatory. That'll be followed by the sky in June. And tonight we have Nigel Goodman presenting his take on it. Then the meeting will stop for YouTube viewers as we move on to our annual general meeting for members only. So that's what we've got coming up. Welcome tonight. We have our 140th member, John Walker. Perhaps members would like to unmute and welcome John. Right, for those who don't know, you can stay in touch with the Society on our website. There's extensive information about us and links to lots of other things. You can follow us on our Facebook page. You can follow us on Twitter. Unfortunately, most of our talks that we've had during lockdown are on our YouTube channel, and you can catch up with those at any time you wish. And what have we got coming up? Well, on the 9th of June, which is next Wednesday, for members only, it's the Imaging and Observing Group. We are hoping the weather lasts, and on the 10th of June, we can do a live stream of the partial solar eclipse from Edinburgh around 10 AM. On the 15th, as I mentioned before, and I'll talk a bit more about it, we have the Losing the Sky event. And on the 18th, Tom Field will be joining us to talk about spectroscopy, a practical approach for amateur astronomers. I think he's joining us from Seattle. And then we've got Professor Giles Hammond from Glasgow talking to us about the photometry of short period asteroids. We're yet to firm up the July talk, but in August, we can all have a month off. But don't let me stop you observing if you wish. So Losing the Sky, this, as I've said before, is a live public discussion by Andrew Lawrence and a host of others. Brian Eno wearing his environmental hat, and Catherine is involved. We've got Matt McCrocken and Amy Mellom as well, and a host of others, all taking part in a series of short discussions about all the aspects that we face in terms of these mega satellite constellations. But that's then, this is now. So I'm going to hand over to Petri Vaisanen, who's going to talk to us about the South African Large Telescope. Over to you, Petri, and let you share your slides.
Thank you very much. Thank you, Andrew. Thanks for the introduction. Let me try to find my presentation here. Okay, so just double checking. You can see this, right?
Yeah, we see it fine.
All right, so yes, so good evening. So nice to hear that it's sunny and warm up there. It is quite chilly and cold here in Cape Town. Yes, so yeah, thanks for the invitation again. So I'm the director of the SAAO, so that's the South African Astronomical Observatory, and SALT is our largest telescopes. A couple of pictures here right away, so I'll explain these a little bit later, but this is from our observing site in Sutherland. And that's where all the action, of course, happens. But the headquarters is in Cape Town. I just have a couple of slides here of just to give you a flavor of what the setup here is. This is a nice picture of our SAAO headquarters in Cape Town. So some of you might have visited, hopefully at some point. It's an absolutely beautiful city, of course, and we're all suffering that you are not coming here as visitors and tourists. I think the city is suffering. It's a very much of a visitor-friendly place, and we have a magnificent site here, Table Mountain, behind over there, and Table Bay, and this is the historic observatory site. And in fact, I'm sitting at the moment inside this building right over there. Privileged enough to actually live on the site as well. I live on that little house over there behind. It's 50 meters away from my office, so my commute isn't that long. Yes, but this is 200 years. This was established exactly 200 years ago by the British. This is our own historic telescope on the site of the Cape Town Observatory, the McLean telescope, with the Table Mountain, Devil's Peak in the background there. And this telescope used to be the largest telescope in the Southern Hemisphere when it was set up in the 1890s. And now the largest single telescope in the Southern Hemisphere, SALT, that I'll talk about in a moment. So there is a lot of heritage and interesting history here, in addition to the modern astronomy, of course, that I love as well. Yeah, okay, I mentioned the history part already. So the observatory was founded 1820. So it was October, we actually had the celebration of the 200 bicentennial in October last year. Sadly, in the middle of lockdowns and all that, so it wasn't quite as festive as it could have been otherwise. We've been SAAO since 1972. So the Royal Observatory was merged with the national facilities here, and it became a South African research facility with the name SAAO. And we are currently part of the South African National Research Foundation, which funds research, but it also has several research facilities, of which we are one of 5. And another one of those 5 is the South African Radio Astronomy Observatory, which then runs what is now the Meerkat and will be the SKA soon. So SAAO and SKA, we're both national facilities here in South African setup. Yeah, so again, I'm actually sitting right behind that window over there at this moment, speaking to you. Right, so SAAO, we're about 140, 150 people altogether, about 25 of us astronomers. We run the telescopes, we do research, and all of that. So we're not usually this color-coded at work. This was from a special end-of-year function, I think a year and a half ago, pre-COVID. Anyway. Right, so just stepping back for a little moment before I go back to our telescopes and facilities, just a couple of them of why do I love what I do? Why do we do astronomy? Why do we build these exciting and expensive, mind you, telescopes and instruments? And part of that is for, images like this, for the inspiration, this from the Carina star-forming region in the Magellanic Clouds. And there's just this awe and inspiration to it. But at the same time, just knowing, and I don't need to go to details, I'm sure this crowd would know about, stars being born at the ends of these clouds, dark, dense molecular clouds, and becoming a star cluster and blowing away the gas. And all the colors, of course, mean different elements: oxygen, nitrogen, hydrogen. And this is what fascinates me, what fascinates people and the general public as well. That, kind of this marrying, this kind of the inspirational, creative way of looking at the universe with high technology. You can actually understand the universe. This is the Cat's Eye Nebula, planetary nebula, so the end result of a life cycle of stars, and that whole thing. It's when you talk to lay people, it's actually inspiring, but at the same time, you're digging into the very nature of the universe. How does it work? Where do we come from? How does it all come together? And obviously, I've stolen this image from somewhere, putting the cosmological equations and the universe. So I'm sort of myself on this right side of this picture. I'm an observational astronomer. I do galaxy evolution myself before I got a little bit too much into management, I think. But this is, galaxy evolution is my field. And then others do the theoretical physics cosmology part of it. But again, understanding the universe, that's what this is all about, and what gives us the kicks. And I think this is why you all are also part of this kind of a society, right? And then the really big questions of looking for, say, planets which might be habitable anywhere close by, further away. Is anybody out there? Really big questions of both for science and philosophy as well. But we can now, for the first time, actually study these kinds of things in a scientific way. It's not speculation, guesswork anymore. But this is what I tell always kids, and if I give talks to school children or high schoolers, that your generation will actually know whether there are planets which can support life in our neighborhood, because the next generation of telescopes will get those spectra, and we actually know. So that is exciting. So just as a wrap up of that part, it's this marriage of curiosity, inspiration with high technology, whatever spin-offs come away, understanding the universe, which I think is the reason why you have observatories and large telescopes. And of course, especially in a country like South Africa, it's really important to show to funders, to the government, and in doing all this, young people actually gather very, very useful skills outside of academia or outside of just this observatory environment, in computing, in big data, big science, machine learning, all of that, for the betterment of the society as a whole. Right. So then off to then the kind of, what do we do here at the SAAO and SALT, and what is the context in this decade of astronomy coming up? So one clear thing is, it's all about multi-wavelength astronomy. So gone are the days when you did only radio astronomy or only optical astronomy or only X-ray astronomy. We all want to work together, because that's how you really get the best information, understand how the universe works. So this is our SALT telescope. This is one of the Meerkat dishes, even further up in the northern Cape of South Africa. And X-ray satellites, gamma ray satellites, putting all that together. So we work in multi-wavelength astronomy. That started already, but that trend will definitely carry further. So I mentioned Meerkat already. It's operating. Well, it's the largest radio facility already in the world, and with expansion to SKA, the whole square kilometer array, it will be humongous. And well, that's actually not so far from you in Manchester, the headquarters of the international SKA organization, SKA Observatory. The telescopes are here in Australia. Then there's multi-messenger astronomy, and okay, I haven't seen your talks going backward, but you must have talked about these things, because it's one of these exciting things happening. Gravitational waves, putting that together with optical waves, has happened a few years ago, 2017. Also neutrinos, neutrino physics, getting optical counterparts from our optical telescopes to neutrino events, and so on. These are the new things which will only get bigger during this decade. Oh, okay, I forgot. I actually had a slide on this this LIGO event from 2017. It's because we're actually very proud of SALT. So I'll come back to SALT later. But many of our telescopes, pictured here at Sutherland, were actually involved in the optical follow-up of that gravitational wave event in 2017. And there was this massive paper, probably a third of the world's astronomers in this one paper, which 3,000-4,000 authors describing the events. And SALT, the spectrum from SALT was the very first one in time. So we were the first one who actually got a decent spectrum of the thing. And then ESO, others. I mean, we're 6-7 hours ahead of Chile, so we had that advantage, right? And we took that into account and put it to good use. And in fact, I was so lucky that I just happened to be at the telescope myself. So I took that spectrum, and it just happened. I was in an observing turn then. So that was a momentous occasion. It was really exciting. And then putting all that data together, those who are actually working in the field. I don't work in this field myself. I was just an observer and reduced the data, but then others physically trying to understand it, getting the first, the light curves and how it's, that was exciting times. But anyway, that was the birth of multi-messenger astronomy, of actually, seeing what you had previously only, figuratively speaking, heard. So putting together two senses and trying to understand the universe that way. Right, other things happening this over the next couple of years. There's the European Large Telescope, ELT, coming up, built by ESO in Chile, 30-meter telescope, Giant Magellan Telescope, JWST, going up next year. I think it is latest launch dates. And yeah, big, huge facilities. And none of this can work alone because they all do their own thing. The big telescopes especially, they have very small fields. They still need smaller telescopes to support them. There's this one, LSST, or what's called Rubin Observatory now. And this is again something I assume many of you would know. This will revolutionize what's called the transient astronomy field by getting hundreds of thousands or millions of new events every night. And this is what I'll talk a little bit later on our response to this, but the basic problem, of course, is that you cannot handle that kind of data quantity in traditional ways at all. You can't call up somebody and say, hey, Joe, can you turn the telescope that way? There's something interesting happening. It's absolutely and totally different ways you have to deal with it. Getting essentially a live video of your sky, of the southern sky, to depths which were previously only the privy of 8-meter class telescopes. So this is coming. You have to be ready for it. And now, so I showed the picture of our headquarters in Cape Town. So from the 70s onward in Sutherland, they put up telescopes. So when I came here 15, 17 years ago, many of these were there already, but probably half of these have actually sprung up over the last 10 years. It feels like this village where every time you go up, there's a new telescope which has popped up. This picture is only from about 2 years ago, maybe 3 years ago, and there's two new ones. There's one 1.8-meter telescope being built right over there, a Japanese one. There's a new NASA Atlas 0.5-meter telescope for near-Earth objects being built right over there. And yeah, it's a great dark site. And that's why the core of what SAAO does is here. And yeah, on the map, it looks like this. So Cape Town headquarters, Sutherland, that's about 400 kilometers away, the Karoo semi-arid desert. And then the Meerkat SKA is even further up in the Northern Cape, in those regions. And if you look at the satellite image over here, you can really see that Sutherland is dark. There really is not much anything over there. Now we've done the sky measurements, and it's right up there with Paranal and Mauna Kea. It's actually more darker than Mauna Kea, but about the same as Paranal. So it really is. It's a very dark site. There's a small village close by, but we have good relationships with them, and they control lighting. So yeah, it's a dark observing site. So the largest telescope in Sutherland is SALT, and SAAO is contracted to operate it, even though SALT is an international collaboration, right? So it's owned by an international consortium, and South Africa is the largest partner, but nevertheless, there's 8, I forget now how many, 9, I think currently 9 partners who own it. This is an unusual picture of having the dome actually open during the day, but we took the opportunity to actually take a picture of it. There was some testing going on. But anyway, so that's the largest single optical telescope in the southern hemisphere. 11 meters, from edge to edge, the primary mirror. Although the effective diameter is about 9 meters, 9.2 meters, in fact, to be exact. Plus the pupil moves. I think I didn't put a picture in this presentation here, but it's the setup is such that, actually, let me go back over here. You'll see this. So this tracker here is in the focal point of the primary mirror. And when you do an observation, you actually park the telescope. The telescope itself does not move during an observation, but the prime focus moves with a tracker, very, very accurately, of course, like the Arecibo radio dish, right? So you have the dish which is in the valley, and then you have this tracker which moves and keeps exactly your target in that same pixel on your detector. So that's how it works, and it works very well. You can track one single object for anywhere between 1 hour to 4 hours, depending on the declination of the source. So it works very similarly to, say, traditional telescopes of VLT. I actually worked with VLT before coming to SALT. So as far as the observing mode, it's very similar. We have thousands of observations in the queue, and at any given time, the astronomer and the operator, they select anything to which might last from 20 minutes to 3 hours, and they select one which fits the atmospheric conditions the best, and then they do it. So you always use the time during the night as effectively as possible. So that's how SALT works. We're in operations in 10 years, 15 years since first light, but about 10 years, 11 years now since the full science operations. So it looks like from inside. It's 91 1-meter segments of these mirror segments, and 3 instruments. I'll very briefly mention the science instruments in a moment here. Yeah, so this kind of, so that the degree to what that primary mirror is tilted to the sky, that actually doesn't change. You rotate it in azimuth, and then the tracker up over there moves. It works very remarkably well. Oh, this was just a fun picture that one of the local newspaper magazines here, engineering magazines, put in when they heard that we're using solar power to power most of the telescope nowadays. And you're studying the stars, you're using star power. There's some beauty in that, in fact. So what kind of science is done? Well, all sorts, everything from asteroids to nearby stars, to galactic, to extragalactic, to cosmology, supernovae. It's just this is from some recent, what our team did, just in kind of an audit of our papers, which they regularly do. But probably about half of the observations are kind of galactic Milky Way type of science. But it really is from wide, depending what the partners want to do. There's some open time as well outside of the consortium things. And this is another one with our astronomy operations team often shows, just want to, when you look at large telescopes and you go to conferences and you compare, you talk how you're doing and what your issues are and so on. The eventual output really is refereed papers, right? If nobody publishes the data that they observe, then what's the point of having a telescope? So people then obviously count papers, and this was just to show. I think it doesn't include last year yet, so it's a little bit old plot, but SALT is sort of generally in that same mixture with the other big, the Subarus, Geminis, Kecks, and VLTs, and so on. Refereed publications per telescope. What I don't show here is that if you'd normalize this by operating costs, SALT would shoot up way over everybody else. Interestingly, so we're quite a cost-effective telescope, and it's probably partially just because we're in South Africa, where the salaries are not, they're not North American, European level. But really, if you count it that way, we are very, very lean producer of science. Okay, but otherwise in this talk, I just don't have time to go to all the science results. And if somebody's interested, I just refer you to from our web pages, from both SALT web pages and SAAO web pages. You can find our annual reports and some recent press releases and so on. And I think I mentioned earlier that a lot of the exciting science nowadays is putting together, say, SALT and MeerKAT, combining some results and understanding, or here SALT and Rosita, looking at supermassive black hole, X-ray, gamma ray, and optical together. Yeah, okay. There's another slide where this was last year from the first simultaneous SALT, MeerKAT. MeerLicht, by the way, let me mention that this is a small telescope in Sutherland. So on that, our plateau optical telescope, which is shadowing MeerKAT. So wherever MeerKAT is pointing, MeerLicht is pointing automatically, always at the same point and continuously taking images, except during the day, of course. So we miss the day part of the radio observations, but at night, wherever MeerKAT is pointing, MeerLicht is pointing and getting simultaneous data. So if there's a interesting, sudden, unknown radio event, automatically you have multi-band optical data of it, and that's an exciting little telescope, and the only one in the world which has this kind of a setup. Okay, I think the final kind of sciencey result thing which I'll mention is this. Few years ago, I mentioned this partially because I was involved in this work, even though it's not really my field. So that's why it really stuck to my mind as an exciting thing. We found from actually totally other data, a very rapidly moving star, which then with SALT, we took the radial velocities and figured out its movement. And nobody else had noticed its curiosity that it had a quite low proper motion, sideways movement on the sky, but very high radial velocity, which of course means that it's, and in this way it was going away from us. So it was going straight away from us. And nobody just had put that figured out or put that thought together that of course it means that it must have been very close to us. And indeed, when you track the motion backwards, about 70,000 years ago, this thing came within the Oort cloud of our solar system. So this is the only known star to have actually visited our solar system. And yeah, that's a whole other story. It was a brown dwarf, actually a binary brown dwarf. But it was so small and went with such high velocity that it didn't. The calculations showed by like in this paper we did simulations that it didn't mess up the Oort cloud in a way that it would have sent a comet shower down to the inner solar system, because that was our first thought. Wow, if this perturbed the Oort cloud enough, you'd have a comet shower coming to the inner. And because, as you might know, that's one of the theories how these periodic extinctions happen on Earth when there's just a period of thousands or tens of thousands of years where there's much more things pounding to the planet than normally. But it looks like this one didn't perturb, so we couldn't put a like a date on the apocalypse about 1 million years ahead. It'll take about 1 million years for these things to come down. So anyway, sigh of relief. Okay, one quick slide of each of the 3 instruments we have on SALT. An imager, SALTICAM. This was built by SAAO. Its special point is that it does high time resolution photometry down to 50 milliseconds. Time resolution, it goes very low down in blue and UV as well. And but otherwise it's a normal imager. So every telescope obviously needs an imager. Our kind of workhorse instrument, especially in the early years, was this RSS, Robert Stobie spectrograph. Does long slit spectroscopy, multi-object spectroscopy, also in high time resolution spectroscopy, polarimetry, Fabry-Perot, all sorts of things. It's like a Swiss knife kind of an instrument. Our next updates on it will be towards the end of this year. By commission next year, we'll get a near infrared arm for it. And then also we're upgrading the visual part of this to have like a single shot medium resolution spectrograph for the full optical field. So this is really needed and desired by the transient astronomy scientist who just want an ID. There's something strange, you don't know what it is, you just want to go and quickly take a deep, good resolution spectrum to understand what it is, the full wavelength scale. So that's what this RSS dual will be. This was built by University of Wisconsin. And then the third instrument built by, again, your neck of woods over there, by Durham University, the HRS, the high resolution spectrograph. And even more so, this has a connection to Edinburgh. I saw Richard Kraken there earlier, and a few years ago, Harriet Watt University built as a demonstrator for laser frequency columns. And so the idea here is that, I mean, the instrument itself does high resolution spectroscopy, but then how good a velocity precision you get depends on your calibrators. You know, how well can you calibrate the observed spectrum? And it turns out that the best ways you can do it is by a laser frequency column, which was built by, hey, your city over there. And this was a really, really nice collaboration a few years ago. And if I remember correctly, this was the first time a laser frequency column was demonstrated on sky at a 10 meter, 8 to 10 meter class telescope, which we're very proud of. And I'm sure Richard and her team there is also very proud of. And moreover, so we've now, over these years, we've demonstrated that we needed to demonstrate the inherent stability of the instrument to really go to decide to buy a full-time LFC. And we've recently made that decision. So we're just now in that process of writing the MOUs and getting the contract together. And but we have the budget for it. Richard, yes, we do. So yes, so over the next year, hopefully there will be a full-time permanent laser frequency column built by Harriet Watt University up at Salt here in Sutherland. That's exciting, because then there's a sizable scientist astronomer community using SALT who are really excited about exoplanets, and this will take the accuracy down from big Jupiters down to smaller planets that you can start studying. Exciting stuff. But overall, okay, I just mentioned kind of the exoplanet type of science. So the way we've kind of made strategic choices of what kind of science we do, and this is relates both to SAAO and SALT. Transients, so understanding the fundamental physics of the nature of the universe using transients, compact objects. There's a long history of this kind of astronomy in South Africa. Galaxy evolution, that's my field, but for Sutherland and SALT, this is important because of those, or why it's smart to do it is because of that dark sky. Galaxies are diffuse. Sutherland doesn't have the best sea, Atacama Desert and Mauna Kea and Arizona even. We're probably similar to La Palma, I think, but this is not the best sea site on the planet, but it's dark. So diffuse objects, dim objects, they are perfect for spectroscopy for SALT, and that's why galaxy evolution kind of things are important. And then we want to get into exoplanet things, and and then we have a computational group as well. Yeah, just a short mention on technology. We keen on technology demonstration things and collaborating. That was what the laser frequency column was all about, for example. But otherwise as well, we have a mechanical electronic workshop here in Cape Town who support our own instruments. But our vision for them this next 5-10 years is to grow that capacity in the high precision mechanics and all of these things, to be able to actually build and bid for competitive instruments elsewhere as well, not only for us, but internationally for other projects. By the way, just as a side, being able to do this high precision mechanics, that was very good for the observatory during about a year ago in the COVID times, because we participated in what was called here the National Ventilator Project. We built together with SAAO. SAAO managed the process. We designed and built prototypes for these oxygen blenders for non-invasive oxygen ventilators, which were needed by the country for the COVID fight against COVID. So in itself, that was very important, of course. But in addition, it actually, during the hardest lockdown, that gave us a good excuse to stay open. And so our workshops were open and we were able to observe throughout. And yeah, curious how these things go. All totally safely, of course, because we were doing observations remotely, but we had an official letter from the government that we were an essential service provider when every other business was organization was closed. Interesting, eh? Right. So Sutherland as a whole, no need to read all through this, but it just shows you a list of telescopes up over there, and you can see there's many countries represented, many different kinds. There's transients, there's exoplanets, this and that. I mentioned right in the beginning 2 new ones coming, a Japanese and an American one. And this is our strength. You know, there's several that we own 100% ourselves, and then there's many hosted facilities, and we have different kinds of agreements with these. We get data from them, or have access to their data, or have access to some of their time, depending on the contract. But there's many over there, and this is something that we want to use strategically. And I think we're going here a little bit against the grain. Many other large observatories in the world have decided to throw away their small telescopes, give them away. They don't want them anymore because they're building 8-meter class telescopes. So we have our 8 to 10 meter class telescope SAAO over there, but we very intentionally decided to utilize this quite a remarkable asset of having so many different size telescopes and different instruments in the same location. And we call that the Intelligent Observatory Project, with the aim of networking all these, essentially turning the whole mountaintop into a single mean machine. You know, say for example, one of the telescopes observes something interesting, or LSST in Chile observes something interesting. We get the trigger, and without that human intervention, then the most suitable of these telescopes would point to it, take the next image, take a spectrum, reduce that spectrum automatically. An algorithm would decide whether that's interesting or not. If it's really interesting, automatically produce what you call a phase 2 observation block and send it to SALT, which would then observe it, right? So this cascading decision tree of making observations, taking data, reducing data, deciding what it is, and triggering the next wave and the next wave of observations. And that's our vision for the several years, and it started already. So part of that project is, well, a big part of that project, as you can imagine, is software development. There's also hardware things at SALT. You can change between those instruments. I mentioned RSS, HRS, SALTicam, just with a click of a button. So just with a command, you can change an instrument. But some of these older telescopes, you still need to go and physically change an instrument. You know, somebody, screwdrivers and whatnot, has to go and change the instrument for 2 hours. And that, of course, doesn't work in the scheme. So we're in the process of building new hardware to have instrument selectors in some of these older telescopes. But that's a very intentional direction that we're taking. And it's called the Intelligent Observatory Project. It goes quite well down with politicians, if I'm honest as well, because it's all of this fourth industrial revolution, and a lot of politicians don't necessarily always understand what it means. But if it's, you know, if it's cool and if it's networks and telescopes and people learning new skills, it's just exciting. But we know it's exciting, and but it's fun to have a project which is, you know, it sounds exciting to also those who potentially fund the thing. Okay, I mentioned this already. So the goal is for a coordinated rapid response in this era of massive deluge of new data, like from the Rubin Observatory LSST survey and multi-messenger astronomy. And we have identified the steps to that. So having remotely operable telescopes, first of all. So SALT is like that already. And we've, over the last year or two, we've converted all of the SAAO telescopes to remotely operable as well. The COVID year was a great push for it, because there was a time that you couldn't very easily travel between provinces here. So during that time, it was the final push for getting all the software together that you could safely operate. Also SALT and all our 3 other SAAO telescopes for the last year have been fully operable from either from the offices here in Cape Town or from the observers' homes. So many times all those observations are happening from the astronomer's bedroom or lounge, wherever they choose to have their laptop in. So essentially we're doing service mode, we're doing remotely operable telescopes, and then the next steps would be robotic capabilities, which we're working on with certain telescopes already. And then the final one, which we're still some way from, but would be this networked autonomous operations. Some of our telescopes have been operated from UK, for example. Some of our observers who are familiar with the operations, we let them do it without coming to South Africa at all. And that's worked well. Right, so we're stepping that direction, definitely. Oh, this is just a screenshot of the teams of that intelligent observatory. Project teams, their systems engineering documents of how will it all work, that there's a central control system and then the control units at all the different telescopes, and and they're at the point of having a couple of software developers coding this one, with then starting from 3 or 4 of these telescopes, which will be first networked and plugged into the thing. And then the exciting thing is that there are other places in the world who are doing a similar thing. And then what you want to do is, do a network of networks. Okay, just in the final few minutes, there's a couple of potential bigger projects for the decade that we're thinking of. These have not been decided yet, but they're being discussed and funding options looked at. One is on SALT. What we call the SALT mini trackers. This is actually started already as a feasibility study. And if I go back to how SALT works, because of its spherical mirror nature, the intrinsic field of view of SALT is actually huge. It's about 100 square degrees. Like it's actually larger than that. It's something like 12 degrees across. So you can see both of the Magellanic Clouds, for example, in one single shot. But you can't use it because it's a spherical mirror. So you need spherical aberration corrector to have it in focus. And that's why we had this tracker that I mentioned, the tracker that moves, and that tracker has a spherical aberration corrector, which is like a barrel-sized optics thing, which corrects a field of 10 arc minutes across for our science use. So that's all the current instruments used in that little field of 10 arc minutes within this big thing. But now in principle, so we have that one big tracker with that one sac. But in principle, you could have many sacs, each with their own instrument, right? And that's what we're looking at. So you have a big thing moving across this field, but maybe it will have 4 or 6 or 8 arms going out, from that main tracker, each with its own smaller spherical aberration corrector, and each with its own camera or spectrograph. And all of a sudden, you turn a 1 10-meter telescope into several, because you can look at many different objects in a very large field. So if you do the math and the optics and the engineering, they wouldn't all end up being 10-meter telescopes, but 5 or 6 or 7-meter telescopes nevertheless, depending on if you're in the edge, you're not looking at the whole thing at the same time, and that's why they're not all. You take the whole thing if you're in the center, but if the arm is too long, then you go to the edge, and it's the effective size gets a little bit slower. But nevertheless, you're multiplying the effective telescope efficiency. So this is what we're looking at, and there are many people excited about this. There's the engineering team working on it, and science case being made, and then we just need to look for the funding part. But there are some instances already who are quite excited if we can show that it works. Another idea, I mean, in parallel, these are not exclusive, but another idea, maybe an additional idea, would be to go for, on the same site, build another 4 to 6 meter class telescope. So of course, many people have those. That's not so exciting in itself, but to really dedicate it for robotic rapid response. So some of you might know there's a really cool project being built to La Palma. The Liverpool Johns Moore University's new robotic telescope, NRT, and like a 4 meter fully robotic one. So we've looked at that concept, and that's something which could be reproduced on the southern hemisphere, because this one will be in the north. Anyway, again, that's something that this SAAO is looking at and looking for potential collaborators. So this is outside of the SALT collaboration, whereas the mini tracker, obviously, it's a SALT collaboration project. But these are a couple of options, kind of step up projects for both SALT and SAAO for the next few years, if we so decide and find the funding. But yeah, I think this might be my last slide already, almost. But just a reminder that this intelligent observatory concept is at the core of the vision of this organization, along with the related technology innovation and building capacity, and starting collaborations with other organizations. And really the strength of it comes from this village of telescopes over there that we either own or our partnership have a partnership in. And okay, I've mentioned previously that it's a lot of work in software and hardware, but you can imagine that it's going to be a lot of work also on the policies and politics. You know, who owns the data? If you're partially owned and all that of that will need to be written down. Otherwise, you'll end up in almighty arguments later if something exciting happens. You have to have the rules of the game written up beforehand, but that is part of the project as well. Cool. So just as a summary, I think the 2020s, for many reasons, many exciting projects, it is a very exciting time for astronomy, for both professional astronomy, but astronomy as a whole, for anybody who's interested in the universe and wants to know what's happening. We feel that we want to be here at SAAO and SALT. We want to be right in the thick of it, both on the science and technology fronts, yeah, being aligned to what is happening in the world of astronomy and keep tabs of what's happening elsewhere. SALT is working well, and we're looking at the next generation capabilities for both on the transients and exoplanet fronts. And again, it's exciting to have that Edinburgh connection there on that exoplanet fronts. And yeah, and then this intelligent observatory and the opportunities that would give if you do it right. So that's all. And yeah, thank you again for the invitation and for the attention, and really hoping that might be able to come and visit. This is a picture taken actually on that evening of our 200-year celebration last October. Yes, thanks very much.
Thank you very much, Petri. Perhaps members can say thank you in the normal way. Now, as far as questions go, as normal, if you're on Zoom, if you'd like to put them in the comments, in the chat section, Peter will call you out. if you're watching on YouTube and you put it in the comments section, we'll try and get through what we can. Just one or two comments before while people are gathering their questions, Petri. We have some direct links in the sense that Thomas Henderson, our first Astronomer Royal, obviously spent some time in the Cape.
Yes.
And if I'm right, Petri Smythe also spent some time.
That's so, right, of course.
So yeah,
yes, Henderson, I knew.
Yeah. It's really interesting. And whilst the questions are still being formulated, I'm going to ask one, as it's my last opportunity to do this in this privileged position I have. The mega constellations and the impact on large telescopes seems to be hugely detrimental. The comments we've had from the Vera Rubin scope that's being built, etc. I mean, what's your position on it?
Yeah, it's especially on things like the Rubin Observatory surveys, anything large with large fields and looking for changes, looking for transients, that is going to be difficult. That is difficult. The effect is much smaller for large telescopes in these kind of traditional instruments, just because the fields of view are so small.
Yeah.
Even with so many more satellites, it's still going to be fairly rare that you just get something through a 5 arcminute field of view. But since we're all going into that kind of science where we rely on the large fields for the input for the interesting science, the trickle effects of the danger comes even down to us or to those telescopes who just do small fields typically.
Yeah. Okay, Peter.
Yes, we have a few questions. Thank you for a very interesting talk, Petri. And the first one's coming from Ian, and I think all of us were wondering about this one.
I'm curious what the function is of what I would describe as the mushroom tower attached to the SALT telescope dome.
Did you get that, Petri?
What was the function?
The tower next to the telescope that looks like a
right. Let me see if there's a. Okay. There's a tower next to it. Tower next to that. Yes. So that's a that tower or the instrument, the center of that, the kind of the bulging thing, right? Inside that tower is right at the center of curvature of that spherical mirror.
Right.
So what is there is a little Shack-Hartmann lenslet system with a laser pointing down. So it's for the alignment of those 91 mirrors. So what happens a few years ago, what happened every night, and actually sometimes even during the night, the operator would turn the telescope facing that tower, and then you put that laser shines a light down to the primary mirror, and you get a return spot from each of the 91 segments. And then essentially you line the spots on exactly on top of each other, right, with software. So then you know that the spherical mirror is all the segments are exactly aligned. Then when temperatures change, the steel structure behind the mirror starts wobbling because of temperature changes. Then the segments misalign, and rather than seeing on your camera one star, you start seeing many stars or even 91 stars if it's really messed up. So then you have to realign. So what happens nowadays, a few years ago, we got an active alignment system. So once you've aligned it using this tower, so we still use the tower, right? So we use the tower for the initial alignment, but now luckily we have an alignment system where if one segment starts going off, the sensing system knows that the next segment, how it's affected, and then you have a massive, inversion math problem to compensate for it. So the edge sensing system keeps it aligned nowadays for many days. So you can go for a full week without a realignment. But every now and then you still need an alignment, and that's when you face the tower, switch on the laser, get the spots, and do alignment. Yeah, so CCAS, Center of Curvature Alignment System for CCAS tower.
Thanks for that, Petri. Will, are you ready to ask your extended question?
Yep, that was excellent talk, Professor Petri. Just a kind of basic question. I'm just wondering what sort of ratio the sort of telescopes are viewing, you know, the sky is being looked at between the northern and southern hemisphere. Is one hemisphere massively different to the other?
You mean in terms of
In terms of sort of large telescopes looking. At, you know, and pointing at the stars, is there one hemisphere which is dramatically greater, or is it kind of split evenly? I'm just, to be honest, I'm not sure.
In fact, nowadays it's actually fairly even. I'd need to count, but it's not that many 8 to 10 meter telescopes, but they're fairly, you know, you have the Keck in Hawaii, you had one Gemini there, you got Subaru, and then HET in Texas. And then in the south, you have one Gemini, one Magellan. Well, okay, 4 VLTs in south. So actually south might be winning at the moment just because there's 4 of those VLT units. But it's okay, Gran Tecan came to La Palma. It's fairly, you know, 100 years ago, it was totally north. Absolutely. So nowadays, it's fairly even, luckily. And to be honest, southern hemisphere is more beautiful. Right? I'm not even biased because I'm originally from the northern hemisphere. Some of you might recognize from my name that I'm actually Finnish. I'm from Finland, but all these years in the southern hemisphere, I mean the southern Milky Way just blows you away.
Oh, fantastic! Thank you.
Thanks for that, Tim. I'm not quite sure what your question means.
It was just in regards to the first question. I just thought it was really interesting to find out what that mushroom-shaped object was, but quite clearly explained.
Okay. Cheers.
Yeah, interestingly, we had a South African government parliamentary committee. They come every now and then, you know, touring the different science facilities. And their question, they mistook that for a missile launch system. We had funny questions about, you know, how does this help in the national defense, and so we were wondering that, okay, do they mean like aliens or anyway?
Okay, John.
Hello, thanks very much for the talk. You said that the seeing wasn't perfect in Sutherland. Is it possible to add adaptive optics to SALT, or does the design prevent that?
Yeah, that's a very good question, and we've looked at it. We've actually thought about it for quite long and hard. There's a couple of studies being made. It does make it well, the segmented system makes it a little bit more difficult. We'd have to what's called phase the segments to really get full advantage of it. But what's called ground layer AO, so getting at least down to the, you know, from our seeing to 0.6, 0.7 arc seconds, maybe that should be easily doable if we chose to do it. But to really get to the diffraction limit of a 10 meter telescope to that 0.1 arc second, that might be difficult. Also because the intrinsic seeing, it's easier to correct good seeing to excellent seeing than to correct mediocre seeing to excellent seeing, as it turns out. So our median seeing is actually about 1.4 in Sutherland.
Thanks very much.
Okay, Ramsey, did you have a comment?
It was about the scanning gantry. It reminded me of phased array radar and sonar, and it's similar to the way that ultrasound scanners work. But it was very interesting to hear that.
Right, that's true.
Okay, and we have a comment from Horst and from Alan, our two well-known experts on other people with South African connection.
Oh, Bob Stobie, of course. Yes. Yes. Yeah. So
in the 70s.
yes, that's right.
Before
Yeah.
it
So
went
sad.
out.
That's right. And of course, that's where the name of our, as you know, and for the information of if some in the audience don't know, the name of our main instrument at SALT is of course named after him. Yes. Yeah. So that is a strong connection to Edinburgh. Yeah. Definitely. Yeah. Sadly, I myself never met him. I came about a year after his passing.
Thank you very much for that. And now it's probably time to pass over to YouTube.
Yep, we've had some good response from YouTube, actually. People from India, Dubai, United States, all over the UK been watching tonight, which has been excellent to see. We've got one question from Pete Briggs. It's kind of follow on from mine, and to see your passion about the Southern Hemisphere. He's asking, is there a need for more large telescopes and arrays in the Northern Hemisphere?
Yeah, it's a good question. I think what I would say is that every time you think of a new big facility, it would be good to think of a certain science case, right? I'm not absolutely convinced that you would need many more large telescope, general user, large arrays or large telescopes. For radio, actually, that would be true because the biggest radio telescope now would become, the SKA will be in the south. So we would be lacking that kind of thing in the north. With optical, it will be fairly even. But I think what's missing is these, like I mentioned in the talk, this very rapid response things. So having large telescopes with some niche thing that they do very well. I personally think that those are more valuable at this point than like general purpose telescopes. As exciting, of course, they would be for individual astronomers.
Excellent. And we had another question, but from AC, but I think you've really, it was about the adaptive optics. So I think you covered that. So that's all from YouTube. Thank you.
Well, I thank you. Perhaps we can thank Petri again. I mean, it was a fascinating talk and filled a lot of holes, certainly in my knowledge of the Southern Hemisphere telescopes in South Africa. Thank you very much.
Thank you. Thanks very much.
And if you want, I'm sure Mark can send you the links for the Losing the Sky session that we're having. And if you're interested, just let us know.
Thank you.
Okay. Thank you, Petri. So it's over to the sky this month, and it's Nigel who's going to give us that talk tonight. So I'm going to hand over to you, Nigel, to share your slides.
Thanks very much, Andrew. Can everybody hear me okay?
Fine.
Good. I'll just start. We've noticed that our internet connection tonight is a bit unstable. So if I drop out just for a few seconds each time, just bear with, and hopefully I'll get through it without any problems. So I'm just going to start to screen share in a moment. Okay, and let's go on to my presentation. Okay, so thank you very much for letting me do the sky at night, the sky for June. And I think the first thing I want to say really that's getting fairly obvious as you look out the window as the nights go on is that it is getting very light, but we're a lot of us are concentrating on daylight work at the moment. So the main event, obviously, is that we are due on the 10th of June in the UK. Certainly, there will be a partial solar eclipse, and we are quite fortunate in Edinburgh that at the height of the eclipse, we will get a coverage of something like 31% of the sun's disk will be covered by the moon. I think if you were further north, if you were at the North Pole, you'd be getting a full solar eclipse. The solar eclipse will be in Edinburgh, from Edinburgh, from our area, will be starting around about 10 o'clock, as Andrew said. It will reach a maximum about 17 minutes past 11 in the morning, which is all very convenient. And last contact of the moon's disk with the disk of the sun will be around about 12:30, just shortly after midday. So we should, if the clouds don't intervene, we should have quite a show. And I will put forward the normal caveats that you should never look directly at the sun if you're observing this solar eclipse with your naked eye, and you should certainly never look at it through any instrument like a telescope or a binocular without some kind of filter. Otherwise, you will damage your eyes, maybe to the point of losing your eyesight. You can purchase online solar eclipse watching glasses. You can simply Google them online, and they are, I think, available £3 or £4 for a pair of those to protect your eyes. And of course, if you're doing astronomy, then you need a suitable filter for your telescope if you're taking pictures. So you need to keep all of these things in mind. Now, as I mentioned before, the big problem we have this time of year is daylight. I think astronomers must be the only people in the world who don't like the summer all that much. We have no proper dark, certainly in June and July, to speak of, certainly not from an astronomical perspective. By late June, there will be more than 17 hours of daylight, with the sun never really getting much more than 12 degrees below the horizon. And just as a quick reminder, we've got our summer solstice coming up on the 21st of June, so our longest day, and that will be taking place at exactly 04:32 on the 21st of June. Just a quick reminder of why it's so important how far below the horizon either the setting or the rising sun is the degrees of twilight. Civil twilight, which is where the sun is between 0 and 6 degrees below the horizon. Nautical twilight comes into play between 12 degrees and 18, and astronomical twilight is beyond that, down to 18 degrees below the horizon, after which it's proper night. And from our perspective, all the way, that's the 1st of June, we can see that we're very firmly in the nautical twilight zone. And when we get to the 30th of June, we're still very firmly in the zone of nautical twilight, which is why we're not getting the kind of darkness that we would like to have as astronomers. So the constellations, they're still there. It's just that they're not as obvious to us because of the intervening light from the sun. And you'll just be finding that you can pick out some of the brighter stars. Certainly with the unaided eye, you'll be finding some of the brighter stars. The main constellation that we haven't seen for some time is Cygnus, is now rising in the east, and that brings with it the summer triangle of Deneb, Altair, and Vega, and that's quite prominent and can still be seen quite easily in the twilight nights. Also high above us, we have Ursa Major, the Plough, with Bootes and Hercules, again quite prominent, and still you'll still be able to observe certain magnitudes of stars in all these constellations, even with the twilight. And of course, the constellations of the winter months are now paying us their last respects and are disappearing down to the west. And to the north, you have Capella beginning to come up as the month progresses, and Cassiopeia, being a circumpolar, one of the circumpolar constellations, again is a very obvious constellation which many people can find quite easily. So the deep sky, is there anything to be done with deep sky during the month of June? Well, yes, even some of the fainter objects can be difficult, but you can still do stuff. I mean, as can be seen by the background to this slide, a wonderful photograph of the Sadr area of Cygnus by Pat Devine. Star clusters, both globular clusters and open clusters, might be good targets, I would suggest, at this time, due to the generally high surface brightness that they have. For example, some of the ones that are available to us at this point in the year, in Ophiuchus, we have M10 and M12 globular clusters. We also have in Hercules M13, the Great Cluster, and M92. This is an image by Jonathan Anderson of one of those clusters. And an open star cluster that I think might be quite interesting to go for is the Coathanger asterism, or Brocchi's cluster in Vulpecula, quite close to Cygnus, and that's an image by Hugh of that asterism. The moon, the phases of the moon may be a little bit difficult during this month, but as has been proven by Mike McGovern, you can certainly image the moon in daylight as well as at night time. So the phases, the last quarter on the 2nd of June, the moon is rising at 2:40 a.m. and setting at 12:29. So the second half of the night, as it were, it will be visible, and it's rising at 4:18 by the sort of later on in the month, by the 10th of June. So it's not and it's also a new moon, so it's going to be very helpful for our solar eclipse. And also on the 18th of June, we're moving into the first quarter with the full moon at the end of the month. The planets, Jupiter was starting to come back into our night sky, gaining elevation in the hours before dawn towards the end of the month. It's in Aquarius and is starting to brighten, reaching an altitude of nearly 20 degrees in the early hours by the last week of June. It'll be in the southeastern part of the sky. And we can see here, this is on the 29th of June at about 3:30 in the morning, when it's, as you can see from this image from Stellarium, that it's the daylight is starting to come back. But it makes a nice, interesting triangle with the moon and Saturn. Also with Jupiter, there are quite a number of Galilean moon shadow transits. If you can get a good image of the moon, of Jupiter, there are quite a number of shadow transits during the month. On the 2nd, Europa transiting the disk of Jupiter. On the 5th of June, it's Io and Ganymede's turn. On the 7th of June, Europa and Io. And on the 10th of June, Callisto, followed on the 12th of June by Ganymede and Io. And the 26th of June, although this will be in daylight, Io and Callisto on the 26th of June, there will be a shadow transit of the disk. Saturn, beginning to brighten, and a close companion still of Jupiter. It will be about 20 degrees to the east of Jupiter through the month, brightening from plus 0.4 to 0.3. Elevation about 15 degrees by 0300 in the south-southeast by the end of June, and beginning to climb towards by about 0240. The planet, if you can get a view of it, if you have a sufficient horizon, the rings are well displayed because it's tilted by about 18 degrees towards us. So the rings are nice and open. And as I mentioned before, it will make a triangle with the waning gibbous moon on the 28th and 29th of the month, with Jupiter as well. And that just that's the 1st of June there. We can see that's one of the coincidences there of the triangle. That's on the 1st of June with looking towards the southeast. Mars obviously last year was but is now diminishing. The disk is getting very small. But if you can see it, because it's quite low now in the night sky, I've got a possible photographic opportunity as it crosses right through the middle of the Beehive cluster M44 in Cancer between the 22nd and 24th of June, which is, but you might be able to see it if you've got a sufficient horizon because it is going to be quite low. And this is just an image from Stellarium looking west-northwest. The Stellarium have this sort of landscape, and you have to take my word for it that Mars is behind that tree, so it's quite low in the west-northwest. And Venus, a number of us were spotting Venus last night, looking very brilliant. It's beginning to come back. And it's beginning to reappear through this month, although as we saw last night, it is still very low and close to the setting sun. So if you're going to take any images, you need a good horizon, and you need to be quick. And just as another possibility, the asteroid Juno reaches opposition this month, and it'll be off to the south, just to the south of Bootes, and again quite low, but might be a possibility for people who like to track asteroids across the night sky. Of course, we're now into the proper noctilucent cloud season, night shining clouds. Throughout June and July, the peak season, as it were, in the northern hemisphere for these types of clouds. And they are, just as a quick reminder, they're made up of clouds of ice crystals, very, very high up in the atmosphere, almost at the edge of space, as it were, depending on where you think the edge of space is. But the point of them is that because they're so high in the atmosphere, that as the sun has set for us on the ground, the clouds themselves are still in full sunlight, so they're still reflecting sunlight. And this results in a sort of very pretty, ethereal, silvery type of cloud, very thin and wispy often, sometimes with colours in what would otherwise be a night sky. And they're usually appearing anywhere between 90 and 120 minutes after sunset on the northwest horizon. or this, a similar time period before sunrise to the northeast. So thank you very much for your attention. I hope I didn't drop out at any point, and very kind of you for listening to me. Thank you.
Thank you, Nigel. Perhaps we can show our appreciation. Well done. That was excellent.
Well done.
Thank
So
you.
somebody might be tapping you on the shoulder again.
Excellent, Nigel. Well,
Thank you.
Oh,
I'm amazed you found that really old picture of mine of Jupiter.
Oh, it's there somewhere.
Let me just try and move on again to the slides. Oh, I've gone through. Just a minute. Right. That's the one I wanted to do. Just to go back as we round up. That's what's coming. Please, if you're watching on YouTube, Losing the Sky is something we want to publish widely, gain a lot of interest and hopefully a lot of support. So I would encourage you all to share either our Facebook notice or our Twitter notice on this, and try and get as much support as we can.